All right, we're going to get started. Hello. We present a method of learning absolute orientation using only relative supervision. When optimizing enclosed manifolds, like those found in orientations, local optima are common. We find that projecting into an open space avoids most of these optima. Specifically, use modified Rodriguez parameters to map from the closed space of quaternions to the open space of R3, and do the optimization in this open space. We find that when you use this method for direct parameter optimization, you outperform existing rotation parameterizations in both uniformly sampled datasets and 1D SFM datasets. Additionally, we find that this work maps to neural network optimization in both rendered and real datasets. If you have any questions about this work, please come by our poster and we're happy to answer them. Thank you.
Hello. As we all roboticists, we know the pain of calibration. So especially in lab environments, the position of the robot and the camera changes a lot. And the calibration is done via markers mostly. In this work, to facilitate this process, we present a learning-based system that eliminates the markers entirely with sub-centimeter position accuracy and sub-decidian rotation accuracy. First, we calculate the end effector pose with two different methods. First method calculates the rotation of the end effector, then using the rotation and the physical dimensions, we calculate the translation, hence the end effector pose. Secondly, we calculate the key points for the end effector, then using key point matching algorithms, we calculate the end effector pose with another way. Then we use ICP to refine both outputs. Lastly, we calculate the pose of the robot space using forward kinematics and the estimated end effector poses. Then using poses from different robot positions, we calculate the final parameters for the robot camera calibration. So if you have any question, please find me in the poster session. Thank you.
So human is not only a teacher of robots. So however, we're asking whether robot can be the teacher of human. So it's common for human to learn physical skills by interacting with partners or teachers. For example, here that we want the human to learn to rotate the plate and get the bomb out of the plate. However, this mode of teaching is generally hard to scale up as it requires one-to-one interactions between teacher and student. So in this work, we're aiming to build a robot teacher to teach human physical skills, thus scaling up teaching. Humans' knowledge, state, and learning behaviors are diverse and hard to represent. Therefore, we need to build a model that accounts for the uncertainty in human learning while being sample efficient. And we further decompose the complex skills that we want to teach into simple sub-skills that we can easily evaluate student performance on. So with these two elements, we can formulate the teaching task as a POM-DP that enables the robot to adapt and reason over humans' behavior. Thank you.
Hi, my name is Danny Dries, and this is joint work with Zhao, Yunzu, Russ, and Mark. We present a framework to learn multi-object dynamics with compositional neural radiance fields and graph neural networks. So the idea of this work is to map observations of the scene from multiple viewpoints into a set of latent vectors, where each latent vector represents the scene each object individually. And this encoder is trained using a compositional neural radiance field. And then having learned this compositional latent space, we can employ a graph neural network to learn a dynamics model in that space. And there we can exploit really cool properties of Nerf to make long horizon predictions much more stable. And in our experiments, we consider both in the real world and in simulation, multiple objects that interact, also rigid and deformable objects. And in general, if you're just curious how cool Nerf is for robotics, you should really come to this poster. Thank you.
Hi, so we explore relative placement tasks where one object must be placed relative to another object, such as the placement of a mug on a rack. Given the point cloud example of the completed task, the robot should be able to do the same task to new objects and new initial configurations. To solve this, we compute task-specific cross-posts or text posts as a transformation required to reach the goal configuration between two objects. To compute this is computed as a function of cross-object correspondences using learned features and point-wise attention weights. We compute soft correspondence to determine which point should be closed, and a correspondence residual for an offset, and learn importance way to define each point's importance for the task. Using all this information, we combine it to compute the required transform. We show our method can generalize from a small number of demonstrations to novel objects and novel initial configurations. Additionally, we also show that our method can generalize across object classes and be conditioned to solve different goal configurations. So please come check out our poster at TextPost. We're happy to answer any questions you have. Thank you.
All right, hello everyone. I'm Dian from Northeastern. Our work on robot learning with Equivariant models tries to answer the question about how should we do real-world reinforcement learning within a reasonable amount of time. So our solution is to use Equivariant method to improve the sample efficiency. The method includes an Equivariant actor function and an invariant created function. The Equivariant actor function's output will rotate with the state rotates. The invariant created output Q value will now change when the input state and action rotate at the same time. The resulting method can automatically generalize to all of the rotated versions of the same state so that sample efficiency is dramatically improved. We show that our method can learn manipulation skills completely on a physical system within 1 or 2 hours. So if you are interested in equivariant learning or sample efficient learning, please come to me. The poster ID is 246. Thanks a lot.
We present offline reinforcement learning at multiple frequencies. To scale up robot learning, we would ideally mix data from different sources together. For example, we may have human demonstration data at a high frequency and robot policy data at a low frequency. This presents a challenge for reinforcement learning because value propagates differently at different frequencies. For example, under intuition, you can see that if we double the step size rate, the value propagates twice as fast. We present adaptive n-step returns to address this issue. The idea behind our method is to scale the value of n with the step size. On the bottom, you can see that when we scale the value of n with the step size, value propagates at the same rate for different frequencies. In all of the environments that we study, adaptive n-step returns improves the performance. This is especially true for low frequency settings where training is usually unstable. Our method also results in more consistent Q values and improves the training stability overall, even compared to individual training. Thank you.
So unfortunately, the author of this slide couldn't make it, so we'll skip to the next one.
Hi, everyone. I'm Maithili, and I'm presenting our work on proactive robot assistance via spatiotemporal object modeling. The aim of this work is to enable robots to assist users with their routine activities without being asked. Specifically, given observations of objects through a person's routine, we enable a robot to learn patterns in object movements, predict their future object usage, and ultimately assist the user by keeping objects ready where needed. Note that we do not rely on human activity recognition, but use object observations alone to gain an insight into these activities. We contribute a graph neural network to learn spatiotemporal patterns in these object movements and create a data set for validation in a simulated household domain, modeling various complex user activities. Our method outperforms prior work by moving 11% more objects to their correct locations and moving minimal unrelated objects. We show the demonstration of our system on a real robot proactively assisting with a morning routine. In conclusion, we show how you can learn patterns in object movements and use that to assist people proactively. Thank you.
Hi, everyone. I'm Charles, and I'll be presenting some joint work with my colleagues at Bear and TRI, as well as MSR. So the goal with our work was to create some sort of method that allows predicting unobserved agents and also planning with respect to them. So if you look at the bottom left, if you're the red car, you not only want to be able to predict that a car might exist in outside of your occluded field of view, but you also want to be able to take action with respect to that. So for example, inching forward to increase your field of view, or perhaps slowing down in anticipation of a potential collision. So we call our method ABP, and it's fully learned from observations. We train and evaluate it using the CoRL simulator. And as you can see in this very large results table, it avoids collisions with hidden vehicles where other similar methods, at least that we think are fair comparisons, are unable to avoid collisions or are less efficient. And yeah, if this is interesting to you, please come by my poster, or if you just want to talk about partial observability and planning. Yeah, thank you.
The world is more than cars and pedestrians, but most autonomous vehicle datasets simply ignore these rare classes like strollers and debris. But if we truly want to build safe autonomy, we must consider how we can detect both common and rare classes. Now, this problem isn't simply solved by adding these rare classes to a state-of-the-art 3D LiDAR-based detector. This gives us 4% accuracy on strollers. And it's intuitive to see why. So if you look on the right-hand side here of the LiDAR input of the construction worker, it's really hard to tell what we're looking at. And we really need this RGBQ to make sense of this rare class. So just imagine that when we want to detect things that are 20 and 30 meters away, this problem becomes even harder with sparse LiDAR returns. So we find that multimodal fusion of both RGB and LiDAR is essential for addressing this long tail 3D problem. And to find out how we improve stroller detection accuracy from 3% to 33%, come check out our poster. Thank you.
Hi, everyone. I'm going to be presenting our work on visuotactile affordances for cloth manipulation with local control. Here, in this work, we first pick up a towel from the ground, grab a corner, and then use our visuotactile affordance network in order to grab an edge in order to slide all the way to the adjacent corner. Once we've grabbed adjacent corners, we can do downstream manipulation tasks like folding and unfolding. We enable this behavior using tactile perception. We have a pose edge estimation network for the cloth edge within the grip that we use for tactile sliding, as well as a grasp classification network that we use in order to tell if we've grasped an edge or not. We use this as supervision in order to train our visuotactile affordance network. Once we've grasped an edge with our visuotactile affordance network, we can slide all the way to the adjacent corner. We do this in two different configurations, vertically and the more challenging horizontal configurations for longer towels. Come check out my poster for more videos and if you want to learn more. Thank you.
Hi, I'm Po Han Lee from UT Austin, advised by Professor Cinchelli. Imagine a feel robot operating in diverse conditions like sunny or snowy weather across different locations like Texas or New Zealand. How do these robots collaborate with each other to acquire diverse data set for training robust vision models? The robots here have different vision models, different data distribution, and no labels for the images. Also, they cannot upload all the observed data, so they can only sample and upload a part of it. We propose a potential game formulation in which the robots collaborate with each other to decide what to upload and a distributed algorithm in which the robots interact with. We prove that our proposed method will reach an optimal solution to acquire any data distribution in the cloud while preserving privacy. Our method also beats state-of-the-art methods on real-world driving data sets like Berkeley Deep Drive. If you are interested in our work, please stop by our poster. Thank you.
Imagine a plane which needs to autonomously taxi to the gate while tracking a center runway line. Today, we would train a vision model along with an end controller to track this line. However, to be robust to operate in real world, the vision model needs to operate in auto distribution conditions like night, fog, and rain. Today's method to train robust perception models are largely task agnostic. They only generate visual scenarios which work with vision models in isolation and might be completely benign for the end task. In our work, we propose a method to generate adversarial scenarios targeted to end controller. For example, on the left, our method learns to automatically perturb the center runway line, making it harder for the vision model and the controller to track the line. We show that adding this data set to training your vision model leads to more robust performance to our distribution data sets on diverse robotic tasks like robotic manipulation and drone delivery. Thank you, and please check out our poster.
Hi, I'm Samin, and the theme of the work that I'm talking about is applying deep learning to a problem within nonlinear controls. So a control barrier function, or CBF, is a tool within nonlinear controls that lets you synthesize a safety filter, which can be placed on top of any policy to make it safe. And this is a super generic tool too. It applies to definitions of safety as varied as balancing a pendulum on a quadcopter, preventing an arm from colliding with a human, and ensuring that a bipedal robot has stepped safely. So the normal workflow for this is once you have a CBF, there's a straightforward, simple procedure to synthesize a safety filter. But the whole difficulty is, how do you design a valid CBF? It turns out this is really hard if the system has input limits and it's also nonlinear and high dimensional, aka a realistic robotic system. So our idea is, let's train a neural CBF in a certain way to satisfy validity constraints. And the result is, in a few hours of training, you can basically get a almost perfectly valid CBF, aka automatic synthesis of a safe controller. Thanks.
Hi, my name is Suresh Nasriani, and I'll be presenting our work on learning and retrieval from prior data for skill-based imitation learning. Imitation learning is a promising way to learn new tasks, but collecting data for each new task is expensive. In this work, we ask, how can we reuse prior robotic datasets to accelerate learning on novel target tasks? We present Sailor, a hierarchical imitation learning method that learns skills from prior data and a skill-based policy for the target task. Now, to train the policy, we retrieve and learn from behaviors in the prior data that are similar to the behaviors in the target task data, enabling us to learn significantly more effective policies. We showcase our method in a real-world kitchen environment where we collect a prior data set of diverse exploratory behaviors. Using this prior data, we're able to learn effective vision-based policies for target tasks like cooking with just 30 demonstrations. Thank you.
Great. So robot learning directly from visual inputs can be incredibly data inefficient. So in our work, R3M, we're looking to pre-train visual representations for more efficient robot learning. And concretely, we're going to start with the Ego40 human video dataset and pre-train a single visual representation that we're then going to use for downstream robotic manipulation tasks like we see here. When doing imitation learning with a small number of demos, using R3M representations improves significantly over existing visual representations and learning from scratch. And using R3M enables us to learn tasks in the real world in visually rich environments with just 20 demonstrations. So we try to set up R3M to be really easy to use. So with just 3 lines of code, you can add it to any sort of existing robot learning stack. And we've actually already seen many works use R3M models off the shelf, including some at this conference. So happy to take any questions at the poster. Thanks.
Hi, everyone. Here you can see that our robot learns a single imitation learning policy to make coffee, and such learning only requires 50 raw demonstrations, where this task lasts for 800 time steps operating at 20 Hertz. So this work is powered by our model, Verda, imitation learning for robot manipulation with object proposal priors. My name is Yifeng Zhu from UT Austin. This is joint work with Abhijit Joshi, Professor Chisholm, Professor Yuko Zhu. So how does Verda work? So in Verda, we assume that the model is given the visual observations of RGB images and robot proprioceptive states. And the Verda gets the general object proposals using a pre-trained network. And once the model gets the object proposal regions, then it can extract the visual features from proposals to get the object-centered representations. And there is a transformer-based policies that determines task-relevant features to compute the robot commands. To learn more about all our laundry list and also our related open source efforts, please come to the poster session at 217. Thank you so much.
Hi, everyone. I'm Min Chang Song from the UT Austin. long horizon planning problem is challenging as it creates a large depth and branching factor. If one of the early actions is made wrong, the rest of all possible future actions can be infeasible, which creates a large number of backtracking steps. So we proposed, so as an example, if robot places 10 water bottles in the refrigerator, if the robot happens to place the second water bottle in the front area, then by the time robot places the 9th water bottle, it realizes that it's impossible. So we exploit the long horizon dependency in task and motion planning formulation. And we propose to learn a data-driven backjumping heuristic policy to identify a culprit variable or a culprit water bottle, if you want, to improve the planning efficiency. So we, in particular, we explore two learning-based models. One is the imitation learning-based model, and the second one is the counterfactual reasoning-based model. Both utilize the graph neural network to learn the geometry of the scene. We show the performance of our method based over the baselines, including the backtracking. So if you're interested in, please stop by our poster. Thank you.
Hi, we present Verda++, a real-world visual tactile dynamics and perception of deformable objects. We assume a high occlusion cases where we can obtain reaction wrench at the wrist and partial point cloud. Okay, so using Verda++, we can perform a state estimation of 3D geometry using partial observations. Given Cartesian displacement, which is an action, we can predict reaction wrench at the wrist and 3D geometry. So in this work, we analyze Verda++ on two real-world tasks, which is spatula and bike chain manipulation. I hope to see you all at the poster session. Thank you.
Hi, we will present our work that is able to learn a generalizable policy to dexterous manipulation. So in the pipeline, we present a demonstration generation approach and also an imitation learning method that is able to generalize to on-scene object and categories. So we will show that how to learn a dexterous manipulation from human grasp pose. So group poses differ from categories and objects, so it is difficult for imitation learning to learn a group policies. So in the visualization, we show that the baseline is not able to perform well on the task because in the visualization, we use the different object from the training environment. And our method is able to generalize well to on-scene objects. And the task is that we want to relocate the object from one location to another locations. Yeah. And we're also able to generalize to on-scene categories. Yeah, thank you so much.
Hi, I'm Jason from Monash University in Australia. Parallel grippers are common in robotics, but their capabilities for in-hand manipulation can be limited due to their simplicity. One method of manipulating objects in hand with these grippers is through loosening the gripper to induce slip. We specifically focus on the problem of inducing controlled rotation. That is the problem of gravitational pivoting. To measure the change in rotation of an object held in hand, we use an LSTM trained on purely real-world tactile feedback from the force-based and tactile sensors with no reliance on vision. We then integrate a grip controller, which takes the angle change and angular velocity estimated by the LSTM as inputs to create a closed-loop system capable of rotating objects held in hand to a given desired angle. We find that through purely tactile sensory inputs, our system is able to track the change in angle of a previously unseen held object with under 5 degrees of error on average. And the grip controller used with the LSTM also has a decreased error in the final angle change of 53% over an MLP baseline. If you have any more questions, please check out our poster. Thanks.
Okay, I'm excited to share our work on SE3 equivariant relational rearrangement with neural descriptor fields. We're interested in programming relational rearrangement tasks directly from demonstrations. We want a system that can generalize to novel objects while still remaining data efficient. Prior work in this area has been limited by an assumption that the placement object in the task is fixed and known. So our work overcomes this limitation. We propose a method based on neural descriptor fields, which enables a robot to perform relational rearrangement tasks on pairs of unseen objects in outer distribution poses while operating from just a small handful of demonstrations. Here in this example, we can see the robot is able to place a bottle upright in a container, irrespective of the pose of the bottle or the pose of the container. We can also use our method to infer sequential chains of relations, enabling multi-step tasks that involve more than two objects by composing the individual relations. For more details, come visit the poster. Thanks.
All right, that's it for the spotlights. The poster session starts now and goes till 10:50 when coffee break starts. Thanks.
Thank you, everyone. The next section will start here at 11:15. Check out the posters and the demonstrations happening.